the idea is to consider extracting or tracing data in language code as a script request, and do this with the least effort we can have, which probably doesn't mean we, maybe the very least effort is you have a language parser and or a compiler, find it on the map, grab it, and pass the source code, use the API, mine the AST, and what you want. So when you don't have this, this can quite happen because either the compiler is not available in the proprietary language, or it's available but for the language with a different version. You have to do this on your own and becoming a genius programmer. So use your own skills and your own abilities to do this. Source tools might be roughly classified in source tools for big problems, which is actually compilation, like parser, has to be available for the whole language, and also for IDEs, which is a refactoring browser or class browser, which actually doesn't also need full language specification. And small source tools I consider search and replace in source code. The generalization of string templates. A string template is a Python standard library for manipulating strings using some meta characters, substitution semantics. And generalization or also specialization is here. There are safeguards. There is some syntax available which guides these transformations. And finally, expression generation, which means you have the grammar and you generate expressions from this grammar, for example, for testing purposes. So I did the first example, which I think it came up in my office a while ago, which is nested function calls. And nested function calls here, I have C code. Not everything which looks nested here is actually a function call. So we have two examples. The first one, F is main driver, and G is outside of the function. And the second one, we have the call to G within F, and that's what we are actually doing. So I think my first almost haptic attempt is to use the regular expression for this. I just did two, but just 5 or 10 minutes, then I came to reason. And so the reason why this can't possibly work is regular expressions can't count, so all the braces, open and closing braces, and can't be matched with regular expressions. Maybe the toolkits which are available are so strong now that they can do everything, but I can't. So I don't master regular expressions at all. I'm going out of the definition. So, building a C grammar and feeding the parser generator is an option, but maybe you have just enough time. So this is not feasible either. It's just too complicated to build a C grammar, and there's also lots and lots of stuff, and which is especially complicated to see in the C specification is type declarations, and you don't need them. So the third try is to handcraft a parser, which is doable, and you create a product pieces counting machine, state machine, and special case something out, like looking into strings and into comments, and or type declarations like struct declarations. And then you write an engine which needs you search through either C code and seek for at least function calls, and then maybe refine the search for nested function calls. So I think you will define. full C grammar, or of course not. That's what I give you now. That's what I created with this, more or less. There are some Schluehr token definition, which is main, the number operator or so, which contains all the packages, all this identifier, syntax, or numbers of strings, and operators, all the prefix operators, comparison operators, arithmetic operators, or so. But this is mostly abstracted away. I don't want to know this, just the name of the identifier. This is a new grammar. So this is my particular view on the C code for solving this problem. And it's actually sufficient for my pattern matching purpose. And I still need Alexa for a little bit of stuff, also some capturing of junk or lexical information I want to ignore. But I think that's doable, and usually you have something like a token structure in your engine, or whichever you use, and you only have to modify it a little bit. Maybe you have to introduce C-style payments. So what I want to have for searching in the code is something like a read.search function, just not with read, but something else, some other library, other framework. And I also want to know how to find a function call and another function call, but this grammar is already sufficient to find all the function calls. So now you have a choice for a parser generator to implement this. I think there are quite a lot. These were just listed on the Python org page, and like Yaki and Ducks. Yet another. I think it's old joke, but old jokes never die. It's maybe PyParsing is a little popular, some people don't Py. I don't know the SESTI parser, and I would also be surprised what recent has to offer. My own approach is landscape, which is a framework which is a little bolder and bigger and wider in scope than I guess most of its parser generators, but also much wider in scope than what I have here. And there's a sub-package which is called source tools. So yeah, I already mentioned this. It's a parser generator by default. It implements a particular parsing method, which is called trace-based parsing, which is somewhat now Westcox from Google implements something like a trace-based parsing for vector expressions. I think this is quite an old technique. I adapted this for all parser generation and all grammars, and I think maybe I will rule this out by better technique, but it's quite interesting. It consumes lots of my time. There are reusable language components which are generated, which encapsulate all the stuff I need to define language. And well, yeah, it's a pure Python framework right now, which has also the opportunity or the advantage to port this to all Python implementations. So PyPy and EuroPython shall also be very good. There are also some disadvantages here. It's a pure Python implementation, so it's a little bit slow on the Alexa parser side, and it's also a little immature. Whenever I do something sophisticated, I have to go into the framework itself and fix it. So, but that's how I create a component. In this case, cpan call is my task. And I also give it a prompt, which is a little strange because C doesn't have something like this, but it doesn't care because whenever you create a langlet, also spawns an interactive prompt, and you can check out at least when you develop a langlet, you always still modify your grammar, check out new expressions, and it's quite nice to have an interactive prompt to just check your parsing. And this is what will spit out, which is actually used when you define a langlet, which is called Alexander, file for Alexander grammar. And the idea behind this arrow is that a langlet can inherit from another langlet or parent, which is, for example, you use Python as your base language, and then you add some additional grammar definitions. So you get a token base, which is a grammar of Python, which is just a standard grammar, maybe from the distribution, and you add some additional rules to this grammar, and from those definitions, token gen g file is then generated, and also the same for grammar. And so this is the way when you have defined this grammar. In this case, we have this already. You can load this langlet into your interpreter, and all the components are this. So the langlet component and functionality is available immediately, which is among them the important transformer, let's say, postgres, parser, and parser. I don't want to discuss this here in the talk. It would immediately require another talk to go into detail, but you see what you get immediately is when you just specify the grammar, you have the tokenize function, which yields a token string. You can pass your expression and get pass tree, which is a nested list here in this representation. You can unpass and untokenize those token strings and pass trees and get the expression back. So again, then you can interact with your new langlet. It's just an interactive prompt. It does nothing here. It just passes correctly. So this little back arrow is just an indication that something is done. There is no compiler, so it doesn't compile to Python bytecode. So it's just not specified. It is specified when you explicitly configure this your compiler, or say I create a Python extension. So now I try another expression which just doesn't work because it's not in the grammar. That is an exception. Now I will briefly talk about how to search using this langlet definition. And my example is using C-object-C from somewhere. It's code speak. I just used Google search, and this was, I think, the shortest URL which fitted on the slide. So the source is right. And code search imports the C search object, the C called langlet, which is loaded. Is passed as the first parameter, and the appropriate symbol, which is not the top level symbol, but the second top level symbol, is used as the specifier for the search. And then I can iterate over code, and it returns or prints out all the findings. So there are quite a lot of findings, and most of it is complete junk. I can't use it. So I refine the search a little bit. And the first thing I want to have is I want to have this nested function call. So I import two functions, which is called find all, and in this case I use just find all, and finds all this funcdef symbols within the pass tree, and print it out again. So it's just a filter on this. And it's still lots of junk because you have now if and while and for statements and so on. and this can be filtered out as well. It's really not much effort. For this I need to find out on the filtered on the count asking item. And then I get what I was looking for, namely this now here violet highlighted internal functions. So this is the whole program I was using for this class. So the grep folder work. The moral is I can define a really simple llama, feed the search engine, the search function of landscape and get the results, and just need to do post-processing, which is just a few lines to get what I want to. Next, I will talk about not search, but mostly replace or substitution. It's quite similar. So the idea was to use a string template or a string template-like class and throw out the meta character, which is I think it's useful when you have a perspective on string, really just as a string. But when you want to do replacements in source code, you have to actually pass or tokenize this at least. This meta character is not defined in the grammar, so it's something needs done. All the transformations are checked for syntactical correctness, and there's also some really lively facility for avoiding name capturing, which is mostly the macro hygienic feature. So the single string I want to consider here is this if statement. Just an example of an if statement, and actually we have tested Go. And I use this code template library to, in this case I use Python as a language. This is more instructive than just using this C function calls. And I load Python as a language into my program, and then I create a code template with Python in this if statement. So what I'm doing is, because I don't have meta characters, I can't do this internally. I bind some variables to names, or maybe also to completely sections of my code, and I substitute them. And what I get out is, in this case, and pass this, you get a tree of the substitution. It's particular reasons like we talked about, mostly for big language transformations. But when you unpass this, you get this if statement with the substitution. And who thinks this is unremarkable? Or who thinks this is remarkable? Yeah, it is. And you know why? This is what we get when we replace with just the string substitution. And this is grammatically wrong. And I don't taught the landscape framework how to transform or how to replace this syntactically in a syntactic fashion. It's just derived from all those internal structure, which is just going into with the syntax definition. So you see why one up, and it immediately knows how to indent, for example, the statement, because this is part of the grammar specification. You don't get this by just the string substitution. So I want to talk briefly about how this is done. It actually operates on the token tree. It's not on the task tree level, which is more complicated. And you see, I highlight here both the token which are marked by this bind operator or bind method. And the idea is to use a device which is called a token tracer. A token tracer is something like a parser. It's maybe even more low level. So the idea behind the token tracer is to use to have start symbol and to have the first set of all those token of this the start symbol, and then going and you select a signal of those available token, and the token tracer gives you the set of all possible next token. Yeah. So all those non-terminals or plus tree nodes become something like hidden information. This controls the token tracer, but it's not available from the side. So you just have a token, a set of tokens which you can choose. You select one token, and you get the next selectable set of tokens, and so on. And this also controls syntactically correctness, just like a parser does. So here we have our token string, which was the initial one for this if statement. And we select our test, and we place it by the token sequence of a plus x equals 2. And we get a final token string. And this gets verified with the token tracer, but the token tracer is replacement mechanism is a little bit more powerful because in some cases there are tokens missing. For example, event or new line, and there is no ambiguity here, and it can be inserted automatically. So it's something like an auto completion mechanism. So yes, I mentioned name capturing. This is a standard example. We find it also in Wikipedia. This is the infamous swap. So I find here A and B, and I use temp for a substitution, and what I get out is complete garbage. And we can't use it. It's not really what we want. So what I'm doing is just find just assign a local name characteristics to temp, and find this to my code template, and get the name out. You can't go really deep on this, otherwise I would learn more about the language, which I've usually done. But it's quite possible to derive the code template and specialize it for programming language like Python, find out what's an assignment in this language, and do those name capture avoiding automatically. Okay, I think this is the last of the topic I'm talking about. It's generative grammars. Generative grammars is, I think, one of the very basic ideas which motivated the usage of grammars anyway, because you can characterize languages using the grammars by means of just producing all the expressions and even the name production comes from there. But when you want to make this practical, you have to do selection, because you can't usually have infinitely many possible expressions, and it's just not doable. So go back to the original C.4 grammar, and want to see how I can approximate this for expression generation. So my first step is to eliminate the loops. It becomes a little too short, but in the next step I can also add, this is now a special syntax for saying, yes, I want 0 or up to 3 expressions of this kind. In this case, it is a comma-separated list of expressions. I will come back to this later, and just want to make it simple here. And but there are other possible problems, which is cycles, which can also expand your expression generator or infinitely, and you get infinite expressions again. There's a little trick I can apply, which is just look at literal, for example, name, or literal at all, and just find out how I can derive the name from some non-terminal, and just substitute this by the very same name. So I substitute on the non-terminal on the right-hand side of a rule by the name of the same rule. So later on, I can still use all those expressions which are generated, which are not finite, by expressions generated by the rule. So I use another library, which is a language expression. Create a language expression object with my EuroPython code in it. Now I will see what I get. And in this case, I use EuroPython call again. I can use whatever non-terminal I have. And I observe something really strange here. So just look at the last expression. That's not really the expression. So my original grammar was wrong, but it didn't matter. Because it's just an approximation of the true grammar. But in this case, I'm a little bit more ambitious and want to have really C expressions. So I transform my fun call rule in this form, and then I get something more reasonable. Okay, sorry. Just the next one. It's also quite bad. There's this one. I think there's something. Well, so this is what I got. When I use another expression, which is a binary expression, which looks also bogus, but in the C code, which is actually used for my purpose, which is correct, I can do that as well. But I can also refactor my grammar, and I get something like this, which I think there's something about this fine. Yeah. And one thing I wanted to talk about, is using multiplicities, and this can be done by injecting a rule into an existing grammar without modifying the whole thing. And what I get now is more expressions, so I need some more. Yeah, I'm almost finished. I need some more. You can get it by just modifying the rule without changing it. Okay. Let's solve the last picture.
Thank you. Are there any questions? Don't be shy. Here you are.
So my first question is, you said that your production was pretty slow. Did you leverage the Python RE module in your desktop?
No. It's all grammar based, and lexing is actually slower than parsing because usually you get more token than nodes of a parse tree. So yeah, I consider re-implementation in C at one time, but now I still have to figure out what was the best approach to parsing it all.
So as in Spark uses Python REs and sample words. I think
Sorry?
Spark is one of the frameworks you showed.
Was Spark among them?
Yes, it was one of them. I thought.
Yeah, Spark. Yeah, right. I think the basic motivation for using for avoiding vector expressions is that there's what you call there's some ordering. So you have to respect the order of all those expressions you pull, and this is not in a context-free situation. You can arbitrarily order the rules without modifying the meaning of the expression. So I think it's easier to use the context-free approach for just for doing extensions. And yeah.
My other question is, what was the motivation behind the generation that you showed up generating the function calls or defining expressions?
Really just checking out if your grammar works. So when you're doing some stuff and you don't have expressions to check your own parser or your own language, you're lost. So creating those expressions, checking them by view if this is what you intended, and eventually modify the grammar. So going through the process I described.